discussion. I hope you had a great week. So for this week, we are gonna discuss about the lecture 9, the FVCOM ICE module.
Mhm.
Before the class, I have received questions from two people. So the first one is from the uh, Jimmy Jimmy on Seal. Would you please see your question in detail?
Yeah, okay. So my question is, I understand that the ice embedding models has submerged ice volume into surface elevation, but I wonder that this embedding sequence happens,
Mhm.
how
Mhm.
how affect the marginal ice flow where ice rapidly melts or breaks areas. Uh,
Mhm.
I wonder that ice embedding method has some cost and numerical instability or the other problems is my first question.
Okay. Yeah, I think I can address your question. I probably wanna later I also find a paper, to show you about that. Okay.
Yeah,
Okay.
okay.
Yeah.
And then second is the ice modules use EVP
Yeah.
method.
Yeah.
So uh,
Yeah.
uh,
Yeah.
this method is not ice only matters,
Mhm.
also uh, plastic and elastic and the others
Yeah.
characteristics. So I
Mhm.
understand that this method is also used for calculate issues. So, uh, but uh, I wonder that if it used in FFCOM, so FFCOM use unstructured grids. Uh,
Yeah.
so this method can occur the other critical problem or not. Uh,
Yeah.
that is my second question.
Okay, that's good question. So yeah, I can. Okay, I will find a paper for you, so I can use the paper to explain to you. Okay.
Yeah, okay, thank you.
Good. Have other
Um,
question?
Next question is from Mingwu Park.
Mm-hmm.
Okay,
Mm-hmm.
to analyze sigma coordinate pressure gradient error,
Mm-hmm.
I conduct a zero pulsing test in a circular basin with a C-mount. All external pulsings were set to zero, except for vertical temperature and salinity gradient. Simulations were run on a single processor to exclude MPI issue. Oh, next slide. The left figure show bathymetry and the sea surface elevation together, and the upper right shows sea
Mm-hmm.
surface
Okay.
elevation, and the lower right show the vertical section of
Mm-hmm.
temperature. The simulation results reveal that fluctuations in water level begin at the seamount summit from the third time step, eventually causing the model to blow up. Next slide. In contrast, when the vertical density gradient was removed, no fluctuations appeared in the model. My question is, why does this phenomenon occur in the model? This is my question. Thank you.
Okay. Yeah. Yeah. Later I will describe what sigma arrow mean. Okay. Yeah. Okay.
Yeah,
Okay.
so these are the two questions that I received before the class. So is there any other question? No? Okay, so
Let me answer the first question. Okay. So I can find the paper first because the question about ice, I need to find a paper show you how why this don't have instability problem. Okay, I want to find the Gauss paper, for this work. Okay, so that is should be should be 2011, I think. Right? I think that should be 11. Do you find this one? Oh, God, yeah. Okay. Yeah. Okay. Let me find the paper. Yeah, I explain to you. Okay.
I will stop on my
So,
side.
yeah. So now I can show the face. I can show the face for you. So four things. So let me show you the paper. Okay. That's the paper you can get from our website. Talk about ice model. Okay. The fourth thing is that's not embedded. Okay, let me answer your second question first, then answer your first question. Okay. You see it over here. You see the speed problem. You see the problem you see here. You look about the equation here. I want to show you. Okay. This idea is we don't need to worry about this one here. So issues here. Okay. So I want to show you this one here. That's the equation here. Okay. This equation here. All right. So this is very important dynamics over there because you can see when you get ice, like a stretch, like a ridge, certainly converging, diverging, the ice breaking. So this practice, we was, assume this follow on the EVP dynamics. That's not a come from me, it come from Hank. So that's why you have to solve that equation. That's an equation not dependent on what the unstructured grid is. Okay, so because you get an unstructured grid over here, so most equation here just try to get, solve the equation here. So you want to get this term, the sigma term. Okay, sigma term. You see here, this like you see this one here. That's you have to solve the equation. So you have to determine the equation here. That's the method. Now, how you check your method is correct or not? Okay, I don't want to go a lot of detail how to solve equation. That's that's is internal stress. Okay, so this is internal stress tensor. Okay, so that's you can stress the tensor inside there in the ice. Okay, ice had internal stress inside, also belong to sea surface or water, but this is followed like an EVP dynamics. But how you see that your model stable now? That reason what we're doing here, the scale should be very small. So that's the reason we assume we had to run. So that's the elliptic equation. Elliptic equation, not the time dependent equation. Elliptic equation. So you need to solve the elliptic equation. You get a convergent solution. Okay, so then the comparison you have to be follow this one. Show look here. You have to follow. Okay, I want to show you what no one picture here. No here. Okay, when you solve the so EPV model, you have to want to make sure everything, that's a stress turn. You have to be in the circle. You leave a circle. Okay, is stress here. If everything was out of circle, your model is that's not stable. Also, not correct physics. I don't want to explain the word circle. What is a no? So that's no like an ellipse circle is. But this stress turn, you have to be match this one. So then we test the model, the method we use this one. We use the time step how to judge it. We find that if you divide the whole time step as 20 time step, calculate 10, you can see the all the calculation the point is the stress was in the circle. Okay, so this way we can ensure, the numerical instability. Okay, when you do the calculation, but that's why this is a very critical issue. But this this also is the internal stress is very critical for the ice breaking. Okay, quickly ice melting. This all had this issue here, but you have to make sure that's stable. But stability calculation, when you develop the coding, you want to make sure every internal stress calculation was satisfied in the circle region. Okay, so that's what we're doing here. I don't want to explain to you. That's to normalize the principal component stress. Okay, we do the benchmark testing. We do a lot of benchmark testing, different cases. They're all in the circle. So that's why no reason the paper be published. And the reviewer said you have to show me how you stress calculation correct, like your question is. That is stable or not. But then that's you have to test that to make sure it's everything certified this. Okay, that's why you see second thing you see when you get an embedded ice model. So does this one really can cause an ice margin region? That this can be caused like a certainly ice breaking over there. If certainly ice breaking related this kind of internal stress for sure. But if internal stress calculation correctly, so you should. I had a movie show you how the ice was, so the changes there. So I think I had a movie, but not in here. You can see this, you can determine, see, how this model embed. But embed things not changing dynamics. Embed things is just have ice, okay? Ice was into the water. Only difference is, so then you get a lateral stress. Because before your ice was the surface, the water in the bottom, so you don't have a no side stress was on the ice. You don't have a side pressure on your ice, right? So this way, so your ice as ice model, only ice and water exchange between the interface. But now embedded water coming, ice get in there, you get a lateral, heat exchanges. So your heat can be exchanged. They can make your melting fast. Okay, like I give the PowerPoint file to you a long time ago. I think the one you can see that. Okay, so then it's one not a cost instability. If you put embedded ice, you can make the model more stable. Okay, because you get a more realistic ice melting because you get the lateral. If ice certainly breaking, right? It's the acid break. You get a piece over there. You get a piece there. So then they just calculation the surrounding each piece how the stress is. So we run a model for embedded ice. So we found the model is more stable than because you get more exchange there. Okay. I mean the most important thing is again the more realistic about the lateral heat flux. Okay. So that's why, embedded ice there, you look about for example, you look about a picture I give you before. I can show you something. I can show you something. I get a long time ago. I had a 2020. I want to show you ice meeting. So you can see I had a I had a okay poster show you. Okay, no, that's not a one. That's not a one. Okay, sorry, that's not a one. Okay, that's not embedded ice one. Okay, that's not embedded ice one. So I'm not sure do do you know which year is it? 2014, right? No,
Uh,
I think I showed it before. I think I'm pretty sure this is before that. I had an ocean science meeting. I do show this one. 14, 15, no. I couldn't remember this one. This is 20. No, I don't think I have. Embedded ice one. No, I don't have. So no, I just remember last time I show you. I give it a PowerPoint to you. Okay.
I
That's right. I
I
think
Yeah.
it is 2016.
2015. Okay. 2015.
16.
Oh,
16.
16, 16,
Oh,
16. Okay. You see I want to show you. Oh, yeah, that's a good thing. So I think I have this one here. This one, yeah, probably this one. Okay. Yeah, embedded ice. So you can see that, if no embedded ice, you can see the ice was always the surface. Okay, the water is the bottom. So you can see this one here's water just where the ice was no ice is just ice formation. So they release salt. Salt just go down here to go moving here. But in embedded ice you can see when in shallow water when the embedded ice when the ice get a formation, ice thickness changes. Then they heavy. There was sink into the water, right? So they make the water become, for example, before it's water, now it becomes dry. In that way, you can see, your all the ice there, you get the models much stable, also dilutes more correctly. Or for just a melting, you get a melting problem. You see, there's a melting problem. If you get non-invariant ice, you get a heat budget here, heat budget ocean, but in the inside, you don't have the heat exchanges. Okay, so then in the okay, then okay, where are okay this paper. Okay, so then what happened? Let me make it bigger, show you. Okay, so you here, you see this is no, not embedded. This is embedded ice. If you embed ice is secret about in the water, so you get a heat exchange just in the lateral direction. But for this one, you don't have. Okay, so then no, the size, no DOE ice model, they make the presentation. They said no, you have the lateral mixing, but you don't have the embedded ice. What they do, they put a bottom. They include more lateral, mix, like a heat budget in the bottom. They said, okay, because we need the counting for ice thickness, they count the bottom. But this one, you don't need the counting bottom because you get a water here, you get a heat exchange between, it's that direction. So then you can see what the melting happened. You can see the velocity, what happened. You see what happened when you get ice formation. You see that this is embedded ice below. You can see you get a more strong outwelling and the offshore croak here. But this one, you see the outwelling slope region is very small. Because your volume never changes. This volume never changes for unembedded ice, but embedded ice changes the volume. Right? So in the same way for here, you see the embedded ice, because you get a lateral mixing here, the heat budget, you can get a more fresh water release when during the ice melting period. But this is why you see everything happen in the bottom. Okay? But the problem, you see the here, non-embedded ice, you see the pressure grading look like this. Then you have the embedded ice, you get a pressure gradient on both sides very strongly. You get a sea level going up. Okay, so I never write a paper. I just show you what I have here, right? So that's why your question said how you handle instability. The problem, we did not find instability issue. Okay, we found it's much stable. Right? That's much stable. For example, for ice drifting velocity, if you know how to embed ice, wind driving there, ice can move it free, right? Based on the wind direction. But embedded ice, they have to consider, in the water movements, is slow, right? For example, you want to see if you try to get your boat more close to surface, have a much less water sink in the water, your boat can move in fast, right? Driving, but however you put your sink more water there, so your boat is moving slow. Okay, so that's what basically you see. But we didn't find a much significantly different. Okay, we didn't find a much significantly different. The reason because of the Arctic Ocean, you see here, that's a non-embedded ice. That's embedded ice. You see that this is observation data. You look about here, this average size becomes smaller by this one, right? Closest one, but still has some problem. But that's not only embedded ice issue. You see here, you see this is what happened. Okay, this is September. You see 2017. You see this embedded ice, you get more ice melting, but in the 2012, that's very significantly reduced ice. This one is more closest one compared to this one. Okay, but not significant change because the ice, Arctic Ocean ice, not like Antarctica. Okay, do I answer your question?
Yeah, thank you, Professor.
Yeah. So I think that your stability, that's okay. Okay, the second question, let me address the second question. Can you show the screen again?
Yeah.
Second question is very interesting. No, first things. No, not for second. That's the second question, not for this question. Second, no, not for, yeah, this already addressed this question. No, the second person question.
Sorry. Uh,
Yeah,
yeah.
for sigma, yeah. First things, sigma Corning error only happen when you consider stratification. Okay, so the reason because sigma error come here is because of pressure gradient. When you calculate hydrostatic pressure gradient, you have a pressure gradient turn. After sigma transformation, they compare the two turn. Okay, so one is no density gradient, another one is related to the slope. But the two turn is the same magnitude, same order magnitude. But then the size is the opposite. So, however, if you have no stratification, right? So this turn baroclinic pressure gradient equal to 0. You don't have an error, sigma error. Okay, that's the question you find. If you remove the stratification, you did not find oscillation anymore, right? The second thing is you have to be careful to understand the sigma error issue. The first thing is you say that you turn off the bottom fraction, right? You turn off the bottom fraction, you turn on the mixing coefficient. However, have you turned in the horizontal water coefficient? Do you turn off the baroclinic pressure, the baroclinic advection turn? You did not turn off, right? My PhD work told you, even had a motion is completely not mixing everything there. You had a forcing, you had something going on the slope. Do you put a forcing in? Do you have a forcing for your case?
Uh, no, I don't
Yeah, you
input
I
any
did a
process.
C amount of circulation. So, uh, what kind of forcing you give?
Uh,
No any forcing?
I don't input or any processing only temperature and salinity vertical gradient.
Yeah. So then you go back to second slide. I think second slide. So this you don't have any forcing. They run the model. They come out of circulation like this way, right? you, that's correct. I want to
Uh,
try to understand you. Okay.
yes,
So you don't get any forcing there. You double check. Double check your certification. If you put the linear stratification, you don't get any forcing there, right? Give any forcing, you turn on the fraction, everything there. So I just wondering how you can get this kind of circulation. Okay. So that's why I should have said you supposedly, if you had a C mount put there, even you put a if no forcing, no anything, you put a fraction off bottom fraction. I just wondering, do you turn off all this turn? I wondering, but otherwise you're not able to so stronger. You see that you get like one single CPU, right?
yes,
No motivation, you do have the circulation. That means you something not turned off yet. Check this, check your setup. You see that you put the bottom fraction equal to 0, right? You put like a quantity diffusion equal to 0. You put like a quantity diffusion equal. They also bear classical pressure. Are you sure you put all turns 0? Make sure that because this look like a okay. What is it? What is it? This is -5. What is the unit?
Yeah, 10 powered by -5 meter.
Yeah, yeah. In the minus a few features, very small, right? But that's if you sigma arrow, your temperature should be changes. That's the temperature always like this. No, when you do in the case, right, you want to output your temperature. Look at your temperature. That your temperature changes, right? No, you look
Oh,
at the
yeah.
movie. That's that temperature. You put the
Temp
linear stratification there. So if you get
temperature
that,
is
sorry.
so temperature is not animation, is snapshot. So
No. Yeah,
uh
I know that your temperature, you get a fraction equal to zero, everything equal to zero, right? That's correct. But but you want to show the movie for the temperature too,
yes,
right? That's why I want to see your temperature change now.
yes.
Okay.
Uh
However, if your temperature change, you know what happened, right? If you assume, I show you what happened. You be really carefully. Do this case. I show you what happened. I draw the picture, right? So if you look at if you slope like this, okay, you get a slope something like this, okay. You put the temperature as a constant over here, right? So if you get a velocity, if you get a eddy calculus zero, right? You see what I mean? So that means what happened? That means you get a temperature flux over bottom like this. Okay? Because you get a zero here, supposedly there's a bottom stress over here, but now you get a zero. So that means your stress equal to zero. So your temperature should keep no change if sigma L, so you should see the temperature change here and here. Okay? So if the temperature changes, so you will ask a question that's what cause temperature changes? The one thing that you can, suppose you don't have any forcing, right? You don't have any forcing. That's why you only run the model there, they see the oscillation like this way, okay, right? So you have to make. I just wondering, do you get the order because I tested before, okay? If you don't have any forcing anything there, even a very steep topography, put linear stratification, the not motion is always its temperature never is changing, velocity very small. Okay, right? You look at my paper there. I show the paper. I show the paper there. You see the paper, right? You see my paper, the 2000 let's see, 2008. 17 can find the 2008 paper.
Yeah, let me find it.
2007, 2008.
It is in one paper's appendix, right?
No, it was in the paper. No, not for Palm model, just for FVCOM model. I compare with the Palm. Yeah, I compare with the Palm model. Let me find this. I'll show you. Make sure you get every setup is correct because the results very, very different. What my understanding. Okay, okay. Let me show you. 2007. Oh yeah, uh, yeah. Here, I found it. Okay,
Uh-huh.
okay. You look at this paper. Okay, I share screen with you. Okay, here you look at the paper. I did a case study, the sigma arrow. You see that here. You're able to see that. See this one here. Here, right over here. So you can see I assuming the case like a cylinder case. I see that I saw the circulation like I put a FV count here, right? I put a FV count here. So then I said, you should be, like case what, 26, okay, 26, which was 26, 26 here. That's a picture. Okay, no, I've computed the Princeton model 26. Where is the figure 26? I show you what my condition is. No, that's all type simulation because of too many figure. Okay, that's a problem. Let me do I find this 20? No, it's here. I put the linear stratification. All right, the case here. We consider cylinder lake. Okay, we had a radio like this way. I consider step 12 at the temperature here. I consider gradings very larger. So then I sort of know because of the boundary condition issue, I said as a pound use like a special temperature boundary condition equal to 0, right? But FVCOM we use the complete FVCOM determine include the Hawaiian diffusion vertically. So then I said I would put a constant background mixing coefficient 10, no temperature flux in the vertically. Okay, so I want to compare the FVCOM results temperature, the slope region, the mixing to satisfy. Okay, so I think a thermal boundary, you do have a thermal boundary come out if you had a boundary mixing coefficient. That's why when you do your model, have you turned off the background mixing equal to 0? Question? Have you turn on the Hawaiian diffusion coefficient 0? Do you put a background mixing 0?
Oh, I turned the mixing coefficient to 0.
Yeah, your equation could 0, however, you have a background mixing there, you can cause the function. You go back and read my paper, okay? Right? Understand what I testing is? So that's why you see that, okay, you can see over here, I see there's a numerical errors of partner can be resolved the structure for the thermal boundary layer. Okay, this you do have a thermal boundary layer if you had a supposedly I test the coding. If I don't any forcing, I put every fraction 0, my temperature never change with time. But the real problem, the sigma error come out, you put a diffusion in, right? So your model should be sure if you set it correctly, you put everything, turn on the mixing, everything. You should not see any changes. I'm wondering something you set up not fully correctly. Okay, not you sometimes you not show off yet. Okay, but then I said sigma error come out when you put limited mixing, for example, bottom mixing, so you can get a sigma error. So then the sigma error, I found it's interesting. No, this one I just want to show the picture here. I want to show if you have a coarse resolution, you do have solution. You don't get result of bottom boundary layer very well. Okay, right? You can see the circulation. So then you see this case here. You can see the resolution become high. You can see all the bottom boundary resolve. Okay, but that's why for constant eddy viscosity I use, right? For this one, but for your case, if you turn on all the time, make sure. That's why experiments I want to make sure you do that. You want to turn off all the mixing. Okay, right? In background mixing, horizontal mixing, vertical mixing, both momentum and the temperature equation. Okay, so if you do this one, that temperature should not change with time. Okay,
Okay,
right?
I understand.
Yeah, you just try to see, please go to try that. Okay, please read my paper. I also had a 1985 paper. I talk about what sigma error come from. Okay, so why you get a sigma error? What happened? How this one? So then you understand what happened. If you have a diffusion, for example, you have a constant area, so then you get a band boundary condition. That's why I want to see your temperature plot with time. Do you show at the bottom boundary layer, thermal boundary layer and the slope region? If you do that, that's mean you do have a fraction in the model. Okay, go back to check. Then we can talk more. Okay. Read my two paper. One is this paper, This is a 2000 paper. Read the case. That's the 2007. Another for I read for Pang's paper, 1995. Okay, 1995 paper. You go to read the two paper. Let me see that 1995 paper here. You can find a website here. Okay, you can find this paper. I had appendix. I want to show you the appendix. I had this one here. Yeah, this one symmetric bank. I talk about sigma arrow. Okay, you look at the paper. You go to appendix. Appendix. Appendix here. Okay, so appendix. You look at not look at this one here. Just put appendix. That's not FVCOM. You look at this one. Look at appendix here. From here. Okay, read it. So read this appendix. Okay, then you can figure out what it can, so sigma arrow come from. So then you can do your testing. Okay, understand testing? That's why you see it over here. I see it's equal to this one linear stratification. If you do the perturbation there, how you determine. So what criteria equation you can get? Okay, vertically be similar like a pound. Okay, so that's why you can see what the thermal boundary layer would mean. Geographic circulation what I mean. So you go to read this paper. Okay. Okay, so you can go download. So then we can come back discussion. Okay. No, we are so busy right now. We don't have able time to go to check your setup to testing, right? But at least they show the temperature. Okay. But then another thing I worry about it because you come out of velocity, you kind of sea level change most 10 to minus 5. 10 to minus 5, I worry about it. That's kind of truncation error. 10 to minus 5 very, very small. Okay, right? Because your Mac model had the arrow something. You want to see the temperature, how the temperature changes now. Okay. If the temperature not changing with time, that means your setup is probably correctly. Then you look about how you get it. So that's kind of, or you make a movie show this one thing, okay, but the problem is how large it is. Okay. All right. So check. I think if you set everything to 0, no mixing everything, you should get no velocity. Okay. Recently we had the testing. I think Jianhua Xi testing the case was about 0.1. 0.1. He put all the forcing F is no velocity. But then the sigma arrow is really problem, you put a mixing on, right? So you're supposed to get a thermal boundary, you don't get it. You get a sigma arrow. This come out, a sigma arrow come out. If no forcing, no fraction, you cannot see that. Right? Because your pressure gradient mostly equal to 0 all the time. Okay. So we'll go back, read the paper, two paper, then test again. Okay. I hope but for your case, I'm very interested. I think you do, very good question, very good question. But make sure you set up is correctly. Okay. Right. Yeah. Your question is good, but I know you see that you put everything's mixing the coefficient equal to 0. You put a mixing coefficient. Now as a start, you don't need to worry. Okay, now as a start, you don't worry because you turn on hazard, you don't need to worry about this one. I just worry about something, you probably not do it consistently. So that's the cause of the problem. You also put a sigma, as a correlation force equal to 0. That's interesting. Okay, sigma arrow not a relative correlation force. Don't worry about that. Okay, but then the mixing over here, you had a CT around here. So that's is the most horizontally. Okay, but you had a vertical mixing. Okay, you have to check a vertical mixing, horizontal, both horizontal mixing, everything there. Okay, so I guess for your case, it didn't shut down all the mixing. Okay, all right. You don't need to worry about non-hydrostatic part because sigma arrow mostly come from hydrostatic. Okay. Okay. So now we changed the method. Recently, I think Siqi had a picture show you. So you can continue pressure method. You see the as pressure arrows, the way comes very small. Okay, the system changes. Okay, but do Siqi you have a PowerPoint here?
Sorry, Dr. Shen. That is on my old laptop. I
Yeah.
use a new one now. I can show it next time.
Okay. Yeah. So when you do the sigma arrow equation, you want to see most of the arrow come out. You put the fraction in, then you get some kind of bottom boundary layer. Then sigma arrow really come out. Okay, it come out the problem. If you don't have a forcing everything fraction every zero, they never move, never change with time. Okay, because there's no sigma arrow should come out. Okay, okay, right. Look like you vodka mixing something not fully turned off yet. Okay. Mm-hmm.
Yeah, so this
So
is a
yeah, another thing that I think is you should be good. You can make your bank is like a little bit flat at the surface. Okay, so this way you don't get a too sharp. That's why you can see the sigma arrows much correct, much easily. Right? So you look like temperature. Okay, see what the temperature how it changes. Okay, good. Any other question?
No, I have no question
Yeah.
anymore. Thank you
Okay.
so much.
Okay. No, any
is
other?
there is there any other question? Any question related to the oceanography?
Excuse me, Professor Chen, I have a question,
Okay.
but it's not related to the ICE module. It's
Yeah.
mostly general,
Uh,
maybe related to the lecture number 6.
mhm.
But I have a question about the I split that we said that is recommended between 5 to 10. I was curious about when we set the parameter like I split, we are representing nature better, or we are mostly trying to keep the model alive numerically. I mean, if a model result change a lot when I split change in our setting, then how much of the result is physical and how much is numerical? Uh,
No, that's very good question. Okay. You know, if you look at ice velocity, right? Ice speed velocity, you look about, I'm not sure I exactly follow the question, but I can, if I see something wrong, you can correct me, okay? So if you look at ice velocity there, you can test that, okay? Most of the ice velocity is really driven by wind, right? But ice drifting, driven by wind. So they get, Arctic Ocean, a lot of observation data show how ice drifting is. The satellite data, you can see how ice moving, but it certainly had no uncertainty in that region. So most time, the model show pretty good in the open ocean, but had a poor performance near the surface, near the coast. Near coast region, you got a problem. The reason because near coast region, you got a faster ice. Okay, the faster ice movement, they also have, had a bottom friction, can be really attack the ice movement. But this kind of mechanism not put in FVCOM current version yet. But I think Great Lake people had a one Ayumi and the Great Lake. He put it as forcing the FVCOM ice model, the new version. He put the ice drifting there. Then he found because we found the ice drifting in the for example Greenland Sea is moving too fast, moving too fast. So then the question come out, so, the problem we have right now is no, you have no satellite data. You do have ice velocity. Not water velocity, ice velocity, right? You do have ice drifting velocity. You can compare model data, but then the problem is uncertainty is a bit larger, right? Your model, like observation uncertainty also your model, because your observation uncertainty is a lot because satellite data, right? So that's why, so your model had a different from the true observation velocity. You don't know should it be correct or not because that's mostly it was inside uncertainty. But only since we understand that in the shallow water, in the near coast region, we do need to make correction, change dynamics because of fast ice issue, right? So you need to consider friction for ice movement. But this is why most of it, we only consider ice drifting two things. One is wind driving, another is internal stress, right? Internal stress between the water body. That's why internal stress of ice can all the ice movement depend on two forcing. But internal stress is also determined on the velocity was in between the ice, we have a paper between the ice and the water. But if the ocean circulation model is circulation not correct, internal stress could be had a big error, right? So that's why we want to, so that it means when we see, okay, should we do the data simulation? The problem, we don't know which one we should assimilate. Right? Because internal stress there, they become velocity shield between ice movement. But most times the ice movement, like driving the ice movement, that's stress a little bit more accurate than the internal stress of the water. Because the water is dependent on stratification. The one issue is very interesting here. In the Wusuo scientists put the drift data. Drifter measures the mixed layer below the ice. They even found a mixed layer in the below the ice can be the 20 meters, 30 meters. You see that the paper they publish, okay? But however, we look at our model results. We find that below the ice water very stable, right? Also, unless you get ice melting, ice melting, right? So they can put the fresh water in stable. And once the ice formation in winter time, they leave the salt. Then you can see the little bit of salt mixing, some hairline. But most time we only get less than 5 meters, right? We only the below the ice, the ocean part, you wind driving, you're gonna mixing wind driving there, so you can get a more deep mix there. That's we understand. But the drift show that below the ice, they're gonna mix there is also deeper. But I completely trust what his observation is because it come from they had an ice coverage, they had an ice signal, they can measure the water drift below the ice or on the ice, right? So they can measure the mix, they do measure like a mixed layer depths there. That's why we don't understand how this can happen. Now, what is the physical mechanism? One suggestion, I guess is a mixed layer caused by lateral advection. Just you have water moving below the ice around circulation like a dry circulation or slope region. You move the water in. This mixed layer waters come from a certain layer in the above layer from surrounding area, non-ice area, the ice-free area. If you only consider ice interaction, right? So you're not able to see that. You don't have no physical mechanism you can cause the deviation. But then the question come on, you run the model. So far we run the model. Most people only include like ice coverage, but don't pay attention to ice thickness. Because ice thickness really depends on how the ice can move, right? So if a thicker one, they move slowly, the thin one, they move fast. But then you look about the satellite data. Now it's beautiful satellite data available, have multi-satellite data. We have a recent published paper. So you can measure the ice thickness. So we compare with a US measurement, not like a satellite data, like an in situ measurement, right? Measurement, they get a different kind of measurement. We compare the Russia data. We get a Russia data too, right? We found 99% of data come from Russia. US only had Alaska coast had a couple stations. But the computer data there, we found so satellite data error is very big. And certainly the error is very big. All right. So we will think about a simulation set that data sickness into the model, make a sickness corrected, then you get a ice drifting more corrected. But the problem is that your measurement uncertainty to set that data is so huge, right? Compared with the in situ temperature data, in situ sickness data. That's why you're hard to determine. But this also affects the ice movement velocity. That's why the question come out, that's a good question. I'm not sure I addressed the question yet. We don't really know how we simulate it, right? We only can stay the life what we have, but then we couple things we need to figure out. The first thing is to know how we can get the mixed layer depth correctly below the mixed layer. But the ice melting depends the freedom temperature and this includes salinity, right? Temperature, temperature determines the bottom temperature. If you get a water moving for the free ice region into there, the water should be much warmer, also much cold, right? So then we found, if you have a lot of water movement inside there, so then the question comes out to how thin we should get the depth in the surface, get the water corrected, transport corrected. If a lot of warm water, for example, like Atlantic water in, like the Arctic Ocean, you get North Atlantic water, that's the warm water in, right? So if we go there, so this you can melt the ice very quickly if you mix it very deep. So a lot of things, to be honest, a lot of things was a lot of uncertainty in the Arctic Ocean, right? So we need to understand for the ice, invent the ice is the one issue we need to consider, but I find it's not very significant important in the Arctic Ocean. Antarctica pretty important because the ice sheet over there, ice mountain, but in the Arctic Ocean not very important. But however, the mixed layer or other dynamics, we still unclear. That's why, so you see should we keep in the modest current, also should be simulated? So my answer is no. If you have current meter data, you should do the simulation. If not, better not do anything, right? Better than anything because if that's the reason you look at the European Arctic Ocean research in Russia, they put like a measurement on the front Strait. They put the measurement on the Bering Strait. But this is two major. Bering Strait has water in. The front Strait has water in and out. Northland water in and the Arctic Ocean get out. But I said, for my opinion, because most people do the Bering Strait, they measure the many years, more than 10 years, but the transport never changed significantly. Okay, only very small, only one switch chopper, very small. They got a net flow for sure. They don't have outer flow, but very stable. However, most significant change in the front Strait. No, not in the water in and there. If you get a current meter data there, you do the simulation, you can really correct the transport in and out from Arctic Ocean. That should be do the data simulation, you can get it right. But inside the Arctic Ocean is hard to do the simulation until you get a very good data. Today I talked to my student there, so we want to do a simulation was in the Beaufort Dry region. But Beaufort Dry also had a sensor, the measurement, not like a buoy. Because you get an ice cover, they're not able to put the buoy that measure current. You know what happened? They put a bottom mounted instrument in the bottom. So the sensor at the time, they started moving up, measure the current, then they're moving down. Okay? They're moving up, then sometimes they come out again, launch again, and when they're just in the water, deep water. I think Professor, like Dr. John too, did that. But then I got to take his data. I got the data, I do the analysis. It's really hard to find what is correctly. Because you get what is, you have the same time, velocity, same depth. But sometimes go this way, sometimes go this way. I didn't find like a beautiful dry circulation people understand that. I also found that if you use a velocity measure, he put a triangle to 3 point. I found a lot of the time is not a clockwise, it's anti-clockwise. So this is another question come on. The people talk about beautiful dry circulation, circulating beautifully, all circulation. So does the beautiful dry really exist or not? Anyway, so I'm not sure I addressed your question, very well, but that's so I will answer probably I don't know the answer is. Okay.
Yeah, thank you very much.
Uh,
Yeah,
Thanks.
so Essen, do you also ask a question about the mode split method?
Yeah, actually,
Yeah,
yeah,
so
but
I
yeah,
found
yeah,
the answer is most interesting for me
yeah, yeah.
about the yeah
Yeah.
yeah also the
Most method I be tell you don't use this most method in it was in the deep ocean.
mhm,
Don't use that. Okay. The reason because most of the method, you run a 2D model, you run a 3D model, right? So
mhm,
your 2D model is a small time step. So you do the averaging velocity every time step. You assume 2D model with transport, you get a more accurate for vertical velocity. No, vertical average velocity, because time step is smaller. But 3D model, you run it for internal time step, the time. If you're averaging, like a internal time velocity, you're averaging with like a small time step barotropic mode velocity, barotropic velocity, you don't get it equal. Okay? You find a 3D calculation vertical average velocity and compare with the 2D model average, not equal. So then the question come out, which one you think is correctly? We believe for transport, 2D model should be better than a 3D model because you use small time step. That's why we make adjustment for 3D model to the 2D model. So we compare with vertical average velocity with the 2D model, 3D model, we found a difference. So then the difference, we want to make sure the two solutions get converging, get a consistency. We have to adjustment. But however, you based on the vertical integrated velocity the difference. So for adjustment, you have to do every level. You cannot see I put the bottom, I put the surface, right? I just put uniformly all the region every level. That's the idea come from Pong, come wrong. They all do it this way. But then the problem come out. You do the one for each cell, right? Each cell. Then, for example, your model show deep ocean, no motion, for example, in the beginning. But now after adjustment, you can see the deep ocean had a small velocity come out, but the velocity is different from one cell to another cell, right? Because this cell point, you do adjustment this cell to another cell, no matter structure, unstructured grid model, they all do the adjustment, right? But adjustment is not a uniform every place. They change it with the node point, change it for the cell, with the cell. But then what happened, because you adjustment for the uniform vertically, so then you run the model for deep ocean, long time. Before the deep ocean, for example, velocity equal to 0. Now you get a velocity also have a velocity different from region to region. You can cause small oscillation. So you look at sea level, you can see a lot of high frequency oscillation come in your model. But this come from numerically. It's not for true circulation. Right? It's numerically. It's just caused by adjustment that cause problem. So this kind of oscillation can really propagate it like a wave. But even the frequency bit high, also emphasis is smaller. But you do see that. Now some people do the M2 tie. They say I feel the ties. Emphasis looks pretty good. But if you look at the cotidal chart, you find it very funny. I found this Arctic Ocean. I found it in the South China Sea. South China Sea at a 4,000 meter deep, 5,000 meter deep region. But when you go to shallow region, most of the model people use it for shallow water, like shallow water, because the wave length is much longer, right? So like a water less than 100 meter, 200 meter, a shallow region, so most of it is not cause any problem. But when you apply the region like a 4,000 meter, you can cause small oscillation. The reason because you adjustment the arrow for all uniform vertically. Now you not adjust for certain level, you just but also you adjustment cell to cell is different, right? I think that
yeah.
most of the model is very technology people like to use because try to solve the sea level problem issue, but now it's So now very few people use it anymore, except the wrong still use it. FVCOM make option there, but all other models don't use it anymore because the deep ocean can cause a lot of problem. Right? But they did not show you, but if you look at the result, you can see a lot of high frequency oscillation come out. That's caused by numeric error, but adjustment. Okay.
Yeah.
Right? Some people say I put some fraction, but how you put a fraction, you don't know how much fraction you need to put it in. Right? It's not like open bond, you can put a sponge layer, can fill the weight, but it's not a sponge, it's not easy. Okay.
Yeah.
Do I answer your question for the most?
Yeah, exactly. Thank you very much.
Yeah,
Thanks.
good. Okay, time is right now.
Yeah. Yeah, it's 2 o'clock. Thank you so much for joining this discussion, and I will upload this discussion video on the YouTube channel. So if you are interested, please review it, and see you next week.
Yeah.
Thank you.
Bye bye.
Bye.
Bye.